Don't worry. Well, thank you for this opportunity. It's a great pleasure to present to AASPI sponsors and community. And right now, what I'm going to present is it's a methodology to calculate reserves or estimate fluids differences using SOM, but based on amplitude based attributes. And I will define what it's an amplitude based attribute. I'm going to contrast it with other studies, and hopefully, I'm going to convince you with some synthetics that SOM works well with ABO attributes. So, as I just mentioned, my motivations is sometimes SOM could be cumbersome in how many clusters we use, and then amplitude attributes could be a lot of them. But in contrast, ABO attributes are a small number in comparison. And then I'm gonna make some tests on how data conditioning impact the results, and I'm gonna compare the volumetrics. And just this is just in rough volumetrics like area of the amplitude anomaly against times or multiplied by thickness, right? So I'm going to show that the agenda that we will be quickly following is the introduction that basically we have been just covering. Some effects on data conditioning, a slight review on ABO attributes, because I think we all know what an ABO attribute is here, but I'm just going to touch base on this so we have a common ground. I'm going to present the self-organizing maps analysis. Later, I'm going to compare the results with the synthetic and some discussion and conclusion. So, as I mentioned, amplitude-based attributes are usually visible in partial stacks or gathers, seismic gathers, and we can create later on our full stack. And with this full stack, we sometimes use similarity or RMS or sweetness or envelope to estimate amplitude anomalies. Um, this is in one hand. On the other hand, ABO attributes are complex, requires a lot of the storage capacity, but also requires a careful calibration with the borehole data so we can validate the IBO response. And my most and foremost motivation is that the list of seismic attributes based on the energy of the reflections is extensive and in times redundant. And using SOM or any unsupervised learning method could reduce the turnaround time in basing to prospect evaluation, because anyone who has made an ABO attribute analysis probably could relate on the fact that when we are capturing geobodies, it's a very artistic way to capture a polygon. So we are representing what the volume is saying. So the data condition strategies, I have tested different different filters. The two of them that are, in my opinion, amplitude friendly are SOF, structure oriented filter, which requires the seismic amplitude, the inline and crossline depths, and a similarity constraint. And on the other hand, the random noise suppressor attenuator, which is only uses the seismic amplitude. We define the filter and the desired noise threshold. So these two are amplitude friendly, and they always need to be considered. In terms of amplitude related attributes, which attributes to select? So the attributes that I'm going to be covering here, or I'm going to be using for SOM, intercept, which is the first term of ABO equations on the linearized fatty or Shui equations, gradients, which is the second term, and curvature, which is the third term. Then a composite attribute, which is the hydrocarbon index, which is basically the intercept minus the logarithmic transformation of the gradient, and the Shui fluid factor, which is a matrix projection on the intercept and gradient. In contrast, trace or single trace attribute anomalies or attribute seismic attributes could be from RMS, envelope, sweetness, the derivative of any of these two, relative acoustic impedances, reflection strength, and so on. So as you can start seeing that there is a lot of redundancy in single trace attributes. In contrast, each one of these ABO attributes means something at least physical. Now, if we take a look at what intercept gradient and curvature means, here, for example, the blue curve represents the gradient. So as you can see, it's a negative gradient. And for all of these three classes of IBO, then the gradient is negative. And then the distance between zero amplitude to the readed amplitude, that's the intercept. And as you can see, this is a positive intercept. This is a slightly positive. I'm going to make a small plus, and then this is a small negative intercept, and this is a huge negative intercept, right? And then the curvature is the derivative of the gradient. So it's basically relates to how fast it is deviating from the horizontal, right? So it's a derivative. It is not the same to have an amplitude anomaly subtle versus having a very sharp amplitude anomaly. For example, I'm going to exaggerate here. So this has a greater or a steeper curvature. And then the hydrocarbon index, as I mentioned, it's intercept times the logarithmic transformation of the intercept of the gradient. And the shear fluid factor is just a matrix transformation of intercept and gradient to remove the mud line or the mud rock line effect. This is what I was just saying. This is a mud rock line. Which represents the fluid or the shaly of the background. And then how far we are, it's the fluid vector. And then the transformation to the fluid factor attribute, it takes an omega, which is the angle to rotate this line into an orthogonal axis, right? So then self-organizing map, it's just a grid projection where on a latent space we have multiple attributes. So it is an adaptive weight technique to represent the data clusters in different grids. So we have seen this example with fruits, with donuts, with pastries, that whatever way we want to describe some self-organizing map, it's an unsupervised clustering technique that it could take into account multiple inputs to represent the whole cluster of data. For example, Julian Chenin in 2022, and in his thesis, he proposed to use single trace attributes to characterize the commercial accumulations and non-commercial accumulation or low saturation gas accumulations. And in his analysis, he did an extensive study using PCA to determine which were the most important attributes, and then fine-tuning the SOM parameterization. So as you can envision, there is a lot of work involved, and he got excellent results. But there is the principal component analysis, then the selection of attributes, which is both time consuming and could be repetitive, right? As we know that sweetness and envelope are linearly correlated, and reflection strength and Hilbert are, if not the same, very close to be the same. And in his results, he compared the King Kong prospect with commercial gas saturation against the Lisa Ann prospect, which was unsaturated gas, and just finding these two neurons or cells, he managed to detect the saturation, the gas saturation presence, right? In contrast, what I'm gonna show is just using pre-stack seismic, or if we already have partial stack seismic, just calculate the ABO attributes, run the SOM attributes, QC the probability thresholds, and then, if needed, do this SOM optimization, or QC the results for reservoir area. So we reduce the redundancy and naturally the time. So the data set that I'm going to be showing you, it's a data set from the Western Australia. It's the Steve Arrow field has around eight boreholes. The first borehole in the center was the one that find the accumulation. Then they drill up deep to continue to find the extension of the reservoir, and then they drilled down deep to find the the oily water contact. Um, and then once they defined it, they limit it with a sidetrack. So it is an amplitude anomaly, yes, but however, it's not completely clear the dimensions of it, right? So near stack minimal extraction um, shows a nice amplitude anomaly, and then the far stack shows again the amplitude anomaly, but the definition of the reservoir is not completed. It is just suggested, right? So I loaded this partial stacks into ASPI. This is again a zoom on the data set. Um, we can see clearly the reservoir here. I did the rejected noise or the SOF to optimize the signal to noise ratio and run the SOM. So a typical representation of an ABO anomaly, it's intercept times gradient. So an intercept times gradient, since both are negative, the result is going to be positive. And as we can observe here, intercept times gradient, it's highlighting the reservoir accurately and with more strength than any other partial gas accumulations, right? So there is naturally a dependence on the quality of the data set or the seismic to input. So running the SOM, and this is just a partial time slides using 5 attributes, which are curvature, gradient, intercept, fluid factor, and hydrocarbon index. We can quickly define different reservoirs, different distribution on the reservoir, right? So which eventually is going to lead to an accurate estimation on the volume. So having a 3D visualization over the horizon of the horizon of interest, we cluster the SOM anomalies, and then we extract just the selected anomalies. So here is the ABO attribute anomaly clustering using SOM without conditioning. With conditioning. This is with conditioning, and this is without conditioning. So there are a few differences. Particularly, I'm going to show this one, and then the fault definition here. So as you can see, using SOF classification, SOF cleaning or conditioning technique, we removed the uncertainty here, and we clearly define the fault separation here. And the volume, it's the area, it's 6.8 square kilometers, and in contrast without conditioning, it's 7.2. Of course, these two areas are increasing the area, and then if we only use single trace attributes, we have all this increasing the area, which is not representative of the reservoir, and it's defining well the fault, but again, it's increasing the area and the thickness. So as I was mentioning, anyone who has done an AVO attribute analysis, doing the cross plot analysis of intercept times gradient, it's complex. We usually require to calibrate this polygon, but we aim to have like the representation of the most anomalous points to capture the reservoir here. This is time consuming and very biased to errors. So to prove that the SOM works, I used a full wave equation to model a wedge model, or to create the seismic representation of a wedge model with different petrophysical properties. So this is near versus far, and then this is the density and S impedance for different reservoir properties. So on the first wedge, you can see that there is a transition between gas, oil, and water. On the second wedge is just the transition between gas and brine. And in the third model, it's just the transition between a small transition between oil and lower porosities reservoirs. So again, I input this into AASPI. This is just the importing the far stack, the near stack. So you can see there is an amplitude difference, and then running the SOM with different neurons or different cluster projections gives me the accuracy, or gives me the transition of the reservoir using SOM with reduction in size, saying that the density is the true model of less than 10%. So using AVO attributes from the partial stacks, I generate the SOM to create a projection of clusters that in 3D and geobody capturing, it's giving me a good representation of the reservoirs. In conclusion, conditioning strategies need to be considered. I think Marcilio also talked about this. SOM analysis based on attributes is more accurate than conventional seismic attributes, and less time consuming. And reservoir characterization using only SOM geobodies, it's a valuable tool to expedite reserves estimation. And I feel that always machine learning model should be calibrated against a synthetic model to see what we are missing. And that's it for today. Thank you for your attendance and your attention. Any questions?